Dear attendees, thank you very much for joining our final event of the EnDurCrete project on the topic of looking into the future of eco-friendly and durable concrete. This event is co-organized by BUP and joined also by our cluster project Resilient, which will be presented. I'm Zuzana Tatyakova from Phoenix TNT, Dissemination and Exploitation Leader for the project, and I will be guiding you through the event. Today, the speakers will talk about the project results, their demonstration, and the future of the eco-friendly and durable concrete. You can see the agenda in front of you. We will have a short 5-minute break in between the presentations. And we have also a Q&A session prepared where partners will present answers to most frequently asked questions on topics which they have chosen. Feel free to contact us, any of the partners, if you have any more questions or need concrete details. All information, contact information can be found on the project website. Let's start with the introduction. Our first speaker is the EnDurCrete Project coordinator, Arno Miller, a senior scientist at Heidelberg Cement. And Arno, the floor is yours.
Okay, thank you, Susanna. So I will try to give you a brief introduction about the EnDurCrete project before we dive in a little bit more details. But before starting this, I would like to give you a first introduction and context. Sorry, I will go to the slide. One back. Yeah, okay. Just to start to tell you how it all started. So actually the motivation and to start with the context is everything that you can see above these images, which is the fact that the production of cement and concrete is actually is responsible for 5 to 8% of the global CO2 emission worldwide, which is relatively significant, and most of this comes from the production of Portland clinker and production of ordinary Portland cement, which has been for a very, very long time, almost a century, the principal structural material for all our constructions. We have a lot of experience with ordinary Portland cements, and we know how to make it. We know it's very well durable, and we know how to make very big constructions. But as with the change of our society, we clearly need now to decarbonate a little bit our industry and produce some concrete with less embedded CO2, which will perform equally or even better than what we have been using by the past. And this is actually the full motivation of the project, and you can see it at the bottom of this slide, is that the research is still needed to develop solutions for sustainable and durable concrete. So this was the whole idea of the project when we started it. So we want to be more sustainable, but also more durable. The reason for the improved durability on top is that, of course, if you're more durable, you will actually postpone the repair or the replacement, which will also then decrease the environmental impact of our industry. So to tackle these tasks and challenges, we gathered together 16 partners. So here you can see all of the partners involved into the EnDurCrete project. And we started a consortium with the clear task of developing new concrete solutions. The project started the 1st of January 2018 and is running over 4 years. So the end of the project is actually next month, so end of 2021. We've got for the full task and for the full consortium funding of 6 million euro for the European Commission. And here you could see the EnDurCrete logo with our goal, which is to develop a cost-effective, sustainable concrete with added value application and improved durability. To present to you very briefly the concept of the project. So I will just move one slide. Can you move one slide down, please, for me? One more. The other side. Yeah, thank you. So just to give you a brief introduction on the concept of the EnDurCrete project. So this here you can see in a nutshell a schematic of what we have developed and what we still work on. So this started by development of novel binder and novel concrete, which we have done a lot of work on that. And then adding to this some concrete solution like functionalized textile, for example, functionalized smart admixtures like nano clay, carbon fibers, biochar, and on top having some multifunctional protective coatings that you can see here in green. So this is the Undercrete project concept. So we developed all these solutions independently first, but the big work of this consortium was also to combine all this technology into final solutions. And you will hear more about each of these technology later in this webinar. Can we move one slide? Thank you. So the project, as you've seen, is actually to combine very different solutions for making durable and sustainable concrete. What we did, we actually combined things in the lab, making some durability tests, durability modeling, but also monitoring. Here you could see, for example, live monitoring of corrosion. But then all of the work done also was meant to be tested in the real world. And for that, we decided to go to exposure sites that you can see here on the slide. So we have chosen 4 exposure sites for our concrete solutions. One is here a tunnel exposure site in Spain. We have also some seawater exposure sites with submerged elements, tidal zone elements, and air elements. We have one site also in Norway, which is similar, but adding on top frost and very cold climate. And then we have a bridge site in Croatia where we place here. You can see the placement of one concrete panel into this area. The idea is, of course, to validate all what we have developed in the lab into these sites. So you will again hear more from the dedicated partner later on during this webinar. So the expected impact is to develop more sustainable concrete and also more durable concrete, as you can see here on the right-hand side, and all of this to be developed together by this big consortium, making also experimental assessment and verification in the lab, in exposure sites, but also developing numerical tool to actually assess our technology also on the computer to have service life prediction. This is my last slide. So here you can see some of the photo of the consortium where we actually gathered together for general assembly meeting. So it's a very big group of 50 people working all together from different countries, different institutions, but also in this institution, we had the local team also working in the lab on the EnDurCrete project. So it's a very big consortium, very big task force onto this EnDurCrete project. We have a dedicated website and we are also present in social media, so Facebook, Twitter, LinkedIn, and YouTube. So if you have not checked them, please go and check what we do. We regularly make some posts. And also, if you have questions after this webinar, you can also address individual partner. You will find our contact into the website. And now I will leave the stage to all my colleagues and the consortium to present to you all of our technology in a little bit more details.
Thank you very much, Arno, for the introduction of the project. Now, as Arno said, we will move on to the presentations of the individual technologies by the project partners. Our next speaker is Gert Bolt, a team leader of the Cement and Binder Technology Group at Heidelberg Cement. So Gert, the floor is yours.
Thank you very much. I would like to present you the composite cement activity at Heidelberg Cement. As mentioned before by Arnaud, we have to look on opportunities to reduce the clinker content in the Portland cement, because this is associated, the clinker production is associated with a high CO2 emission. And the new standard EN 197 Part 5 of the European Cement Standard gives us a lot of possibilities, more compared to the EN 197 Part 1, to lower the clinker factor or clinker content in the cements. And what is the problem when we lower the clinker content? It's the strength development in the cement. As you can see here on the left side, the 2-day strength of an OPC compared to a mixture where we replaced 30% of the OPC clinker by quartz, which is a non-reactive constituent. And because of the dilution of the clinker, we have much lower strength development. If we take reactive materials, which are described in the cement standard, for example, granulated blast furnace slag in a mixture with 10% limestone, we have a very tiny effect on the early strength development by these constituents. But on the right side, you see the graph for the 28 days. And after 28 days, we have a significant improvement in strength because of the reactivity of the slag in combination with the clinker and the limestone. But even there is a gap which we have to close. And the way to close this gap, what we observed is the technology of separate grinding of the materials. The last 100 years, most of the constituents in the cement were co-ground. And now where we are looking for lower clinker factors, we have to go in the direction of separate grinding, which means we have to grind every material with respect to the grindability and the reactivity to the best fineness to replace at the end the most of the clinker. If you work in such complex systems with 3 different materials in grindability and in reactivity, it will take a long time to find the right places where to place your recipe exactly. And there we designed a computer model where we end up at the end with the result that we can replace, if we find the right fineness of the material, we can replace 50% of the clinker by a mixture of 30% slag and 10% limestone without significant impact on the cement performance. And at the end, I would like to show you here the result when it comes to recipe and to the strength development in our project work here. And these are the SEM2CM cement and the SEM6 cement, which we then delivered to the partners in this project for the activities for all the test and durability aspects tests and for the demo sites, where we will get the presentation now from my colleagues. That's from my side for the moment.
Thank you very much, Gert. Our next speaker is Nikola Mikanovic, a principal scientist at the Global Research and Department at Heidelberg Cement, who will present the concrete and admixtures. The floor is yours.
Thank you, Susanna, for your nice introduction. I'll pick up on basically a cement development and inform you about concrete and admixtures development in the scope of the EnDurCrete project. So the concrete development itself, I would say, had a central stage or central part in the project itself. So this was a part of the project where we basically took these novel cements developed in the work package 2, and these new exciting new additive technologies you will hear more about from my colleagues, and we brought everything together into the final product, which is basically EnDurCrete. This concrete was then tested in the work package 5, for durability in the lab. And then we rolled out, upscaled the concrete production in work package 6, produced the elements to be placed at the actually demo at 4 different demo sites. The whole development went into the 3 basically simple steps. In step number 1, what we try to do is to develop EnDurCrete mixes with novel cements only, which were developed again in work package 2. And the development of concrete recipes was based on our design and production requirements, which we got from the work package 1. And the end results was basically 3 different concrete types containing a new cements, a marine concrete mix, which was intended to be tested at 2 demo marine sites, one in Spain and the other in Croatia. We have one tunnel mix intended to be tested at the tunnel demo site in Spain. And we have developed one offshore concrete mix, if you want, to be tested for offshore application at the demo site in Norway. Then in the second step, we try to incorporate basically these novel additions and additives into existing concrete compositions. But before we did that, we try to figure out what's the impact of these additions on fresh and hardened properties of the concrete. The focus was on actually workability and strength development, and we try to incorporate a nanoclay corrosion inhibitor and 2 types of carbon-based materials, basically char and recycled carbon fines. And the study on the compatibility of these additives with the concrete was done by Sika, and what they figure out is that these additions, they have a negative impact on the workability, and this problem was solved by Sika. They provided a tailor-made polymers and admixtures to basically solve these concrete performance issues. When it comes to the strength development, we saw that the carbon-based materials have more or less no impact, but this nanoclay corrosion inhibitor has a negative impact at the strength development. So for this reason, we decided to only test this nanoclay at one demo site. I'll get back to this on one of my next slide. So here is the summary of the step 3, basically concrete compositions with novel cements and novel additives. So these are the compositions containing carbon-based materials intended to be tested at a marine site in Spain and a tunnel demo site in Spain too. We don't have obviously time to pass through this, but what is important is to see that in fresh and hardened state, there is no impact of these additions on performance of the concrete, and this concrete fulfills all design requirements. These are the 2 other demo sites and the compositions which we decided to basically test there. So you can unfortunately see that the concrete compositions containing a nanoclay, so this is this marine concrete, that 1% of nanoclay has a negative impact on the strength development at all test stages. But we are reaching 40-45 MPa, which is basically limit for a marine mix. And for this reason, we decided to basically test this concrete at the Kirk Bridge demo site. When it comes to the offshore concrete, the impact of the nanoclay was even actually bigger. So for this reason, we decided only to test the composition containing actually novel cement. This is basically my last slide, just to tell you that in the scope of this work package, we haven't only developed concrete mix designs, but we also helped lab preparation for the lab testing in the scope of the work package 5 and rollout of developed solutions, which occurred in basically work package 6. So this is all I have. Thank you. Thank you very much for your attention.
Thank you very much, Nicola. Our next speaker is Margareta Laccia, from a senior engineer and innovation manager at iBox, who will present the nano clays. You're muted. Please unmute yourself.
Okay, now, so good morning, everyone. And today I'm going to explain to you about what we have done so far and with the company EnDurCrete and the nano inhibiting additives for the corrosion. EnDurCrete is a consulting micro SME located in Spain, in Valencia, and we are focused on developing maritime port technologies through 2 research and development areas. The first one is about advanced materials, and the second one is wave energy. And all this activity has granted iBox with a recognition from the Spanish Ministry of Innovation with Innovation Seal since 2015. So our product is a corrosion inhibiting additive, and the knowledge on these nano inhibitors is based on the development of a former company called CIES Infraestructuras, which disappeared. But before disappearing, we signed an agreement with them in 2014, and where iBox would be in charge of all the technological development and exploitation of the corrosion inhibiting additive. So our inhibitor prevents the occurrence of the corrosion processes in structures exposed to marine environments or in areas where de-icing salts are used. And we achieved the Spanish patent it was published in May 2019. And this is the full background. And now let's go to the project. So within EnDurCrete, the objective was to develop a product that will act as an intelligent reserve of corrosion inhibitors in reinforced concrete, which can be released only when there is a danger of starting the oxidation processes of the reinforcement. So the fundamentals of these inhibitors that we call Chlorides, this is the name on the slide, is that they are laminar clays that are modified with selene groups and anionic corrosion inhibitors for the prevention of corrosion in reinforced concrete. These developed additives respond actively to the presence of chloride anions, which cause corrosion in concrete, releasing the inhibitor anion in the presence of high concentrations of these chloride anions through an exchange mechanism. So iBox participated in task 1. During this task, we reviewed the requirements of some regulations for marine environment specifically. And our main task was work package 3. We were leading 3.1 named Development and Optimization of Smart Corrosion Inhibitors based on nano-modified clays. And the aim of the task was to develop and optimize the novel additive to be implemented in concrete mix designs, developed specifically to comply with the requirements defined in work package 1. So for a competitive product, we have to achieve that the inhibitor had to be a maximum of 1% of cement weight. The price will be less than the current commercial solutions, what would be around €2/kilogram, and the performance will increase the lifetime of the concrete or the time corrosion damage it takes to appear up to 3 times. So during the task, the goal was to optimize the proportion of modifier and corrosion inhibitor to fit the concrete requirements and not modify the hydroton kinetics of cement, which was a problem. And in this sense, and with the help of Zika, we were reducing the amount of modifier saline, an anion inhibitor of corrosion, and it was possible to prepare a product. Out of 7 samples, we achieved 1 sample that did not affect, not delay the hydroton kinetics of the cement. And another challenge on this work package was to be able to scale up the production of the inhibitors in quantities close to the kilogram in one reaction, because it will allow to supply large quantities of product to the project partners. So we, at the end, we achieved all these challenges. And in this diagram, you can see the steps for the synthesis of the smart corrosion inhibitor. And yeah, again, what the main work was to find the proportion of modifier and inhibitor, so in a way that they were optimized. So, so during this work package 3, the technology was tested in concrete, and it was proved with anti-corrosion properties and did not have any negative effect on mechanical resistance and other concrete properties at first. But afterwards, it was decided that there were some constraints, and it was only going to be proof in marine environment and not in offshore. But anyway, in our results, as you can see, as time passes, the results are better. So it's a specific product which it performs better as time passes. So here you have some images of the test developed from cement paste, mortar, and concrete specimens. And yeah, all the goals on work package 3, most of them we achieved. To sum up, for work package 6, it will be later explained by our colleagues from Acciona. But then in this upscaling, the inhibitors were ready, and it was time to start with the pilot scale. And the first challenge arose during the upscaling, and was that the consumption energy during the production process was high, and we have to optimize that. And so the results that we are having so far are the same that on work package 3, and Acciona will explain later. But it seems that at first there are not so much significant performance of the inhibitors, but as time passing, it performs the better. And so you have here, well, some graphicals, but again, as I said, the graphs, what they are saying is that, as you see here, as time is passing, the resistance is getting better at 12 months than in 6 months. So the corrosion, it seems less. So that's all so far. We need more time to see the performance of the inhibitor corrosion inhibitors, but at this moment, we have to wait. And price also on the production process was not €2, but it's still on the range of the commercial products. And so we have to wait for the results. And thanks so much. That's all. So next one.
Thank you very much, Margarita, for your presentation. Our next topic is carbon-based additions for self-sink concrete, presented by Francesca Titarelli, Professor of Materials Science and Technology at the University Politecnica della Marche in Italy. The floor is yours.
Okay, thanks Susanna for your kind presentation. Good morning to everyone. The Università Politecnica delle Marche, placed in Ancona, Central Italy, on the Adriatic Sea, participates in the EnDurCrete Project with 2 groups, the mechanical and thermal measurement groups and the material group. Next one, please. Next. It is well known that the continuous monitoring of concrete structure to detect deterioration as soon as possible, some defects, allow to reduce management cost of the structures and to increase its safety. Self-sensing is the ability of a material to perceive its own condition simply by measuring its electrical resistivity, such as water penetration, aggressive substances penetration, strain, Sorry, but I have some problems with the control of the presentation. I'm not able to move up and down.
Just tell us when you need the next slide. And
Thank you, Max. So in this context, self-sensing is the ability of a material to perceive its own condition as cracking, water-aggressive substances penetration, and strain by simply measuring its electrical resistivity. Compared to other traditional monitoring system based on a multi-sensors approach, self-sensing concrete is able to detect multiple phenomena in a cheaper and less complex way. Please, next. The self-sensing concrete properties can be enhanced by decreasing its electrical resistivity with the addition of conductive admixture. In fact, in this way, giving the higher signal to noise ratio, low-cost instrumentation can be used with the possibility of creating real measurement networks with nodes distributed on the wall structure. Next, please. Carbon-based additions are excellent for self-sensing concrete. However, those actually available on the market, such as carbon black, carbon nanotubes, graphene, and carbon nanofibers, are not sustainable, very expensive, and sometimes very toxic. Next, please. Next. Therefore, in the EnDurCrete project, these commercial carbon-based additions for self-sensing concrete have been replaced by innovative, low-cost, carbon-based byproducts, such as biochar by thermal treatment of biomasses and recycled carbon fibers by cutting and milling carbon fibers, panels, and fabrics. Next, please. Next. The experimental results have shown that the joint use of these low-cost fill fibers, even if it does not affect significantly the mechanical performances of concretes. Next. They decrease its electrical resistivity. Next. Next. Giving the possibility of exploiting the self-sensing performances of concretes in terms of next, carbonation, chloride penetration, and water absorption. Next, please. Next. Therefore, in the EnDurCrete project, a low-cost monitoring system which uses self-sensing concrete blocks manufactured with these low-cost carbon-based byproducts have been manufactured and tested in 2 different demo sites, Porta Musele in Gijón and a distributed sensor network has been realized with the measurement nodes installed in the elements to be monitored and then connected to a central hub. Data are available on a cloud through Wi-Fi network or LTE modem. Next, please. A mobile application, next please, has been also developed, which after selecting the demo site, the concrete panel, the parameter and the time interval, shows data as a graph that can be saved in a CSV file to be sent via mail. Results related to the data acquired for approximately 10 months confirm that the signals measured in the panels with conductive additions have a higher signal-to-noise ratio with respect to those measured in the panels without additions, confirming the results obtained at lab scale. The low-cost monitoring system did not show any faults during the demo test activities, and finally, data were not affected by any issues due to the aggressive exposure. Thanks for your attention.
Thank you very much, Francesca, for your presentation. Our next speaker is Paolo Corvalia, Materials Engineer and Project Manager from RINA Consulting. Go ahead.
Thank you very much, Susanna, for your kind introduction, and good morning to everybody. Should I have the control? Yeah, okay. Textile reinforced concrete is an innovative cement-based composite material exploiting the non-corrosive nature of fiber materials for realizing slender and durable concrete elements. And in the EnDurCrete project, we further innovated this concept by embedding a fiber optic sensor inside these panels, and so providing them with a built-in structural monitoring capability. The final goal is to realize a modular sensorized solution like this that you can see in the slide, so that when you are on the field for installation, you just have to connect the two adjacent panels by means of an external optical patch cord. Let's have a look to the components of the system. The textile is made of alkali-resistant glass with a mesh opening of 3 centimeters, while the sensor system is made of 2 distinct cables. Here they are. The blue one is a strain-sensitive cable with roughened surface for a better adhesion with concrete, while the red one is a strain-insensitive cable for thermal compensation. So, in order to set up the production technology and to characterize the performances, we designed and produced 2 samples. The sample A is the reference one, made of ordinary reinforced concrete, while sample B is similar to sample A, but with the replacement of the steel net with the textile. Here are some steps of the production of the samples. Here is a textile preparation, then sensor fastening to the net, sensor protection by means of plastic ducts in order to withstand the concrete pressure, the preparation of the mold, then concrete casting, and finally the molding. While these pictures are related to the application of standard optical connectors at the end of the fibers. The panels were then tested in 3-point bending test. Here you can see some details of the setup, and here the main results, namely the strain profile along the panel at increasing load. We can comment that the strain pattern shape is as we expected it, and also that the strain values we measured are comparable with those obtained by reference electrical strain gauges. If we look at the load deflection curves for a comparison of the mechanical performances, we can see that the TRC solution provided enhanced ductility about plus 30%, and also enhanced the load carrying capacity with plus nearly 40% with respect to the traditional, let's say the benchmark solution. So the final step of the work was the production of two prototypes, modular prototypes conceived for a tunnel application. Here you can see some pictures of the production, and here are the two modules placed inside the mining tunnel in Spain. And here you can see the connection, the optical connection between the two modules, which was successfully tested. So this was actually a real demonstrator of the concept I mentioned before. So let's go to draw some conclusions. We developed and tested textile reinforced concrete panels sensorized with distributed fiber optic sensors, with the final goal to develop a modular concept of self-sensing components. We found that the sensors survived the production process and provided consistent data up to advanced cracking stage. Also, the TRC solution provided enhanced ductility and load carrying capacity. And finally, we demonstrated this technology by large-scale prototypes in real tunnel environment. So that's all from my side. Thank you very much for your kind attention.
Thank you very much, Paolo, for your presentation of your work. The last presentations in this series on the project results, we have Maria Papa, manager at the Research and Development Department of AMS Solutions, presenting the coatings. The floor is yours, Maria.
Thank you very much, Susanna. Hello, everyone. I am Maria Papa, and on behalf of AMS, I will present you the multifunctional coatings developed in the framework of the EnDurCrete project. Apologies, but because I have some connection issues, we decided to keep my camera off in order to secure the audio. So the developed multifunctional coatings, which actually are paints having polyurethane as basic material, aim to serve the following needs. First of all, to offer protection to the concrete structure that they covered from long-term exposure to the environment. So they aim to be resistant in weathering, wear and tear, and exhibit waterproof activity and an increased durability. Secondly, to reduce the maintenance needs in order to eliminate the frequent repaint or replacement of the damaged coating. Also important to be a cost-saving solution, as through protection and through durability, we save raw materials and we reduce labor and energy costs for the repairing or repainting. Also to be a low-cost solution. And finally, its application to be rather simple, for example, through spraying, and to be done by non-specialists. And the basic activities of these coatings are achieved by means of combined properties, self-healing properties, self-cleaning properties, photocatalytic properties, anti-molding properties, and water-resistant properties. The multifunctional formulation includes a commercial polyurethane paint that serves as base for the formulation, self-healing agents that for the final formulation were chosen microcapsules of 50 microns containing polyurethane paint that were synthesized by AMS with a microencapsulation method, titanium dioxide nanopowders of the Degussa P25 grade, as well as a mix of anatas and rutile titanium dioxide for the self-cleaning, photocatalytic, and anti-molding properties of the coating, silver ions, and small quantity of an antibiotic for the anti-molding properties, and finally indium tin oxide nanopowder, which in this case serves as a stabilizer of the formulation towards the impact that the solar radiation can have on the system. The developed multifunctional formulation was evaluated in the lab regarding the self-healing activity by scratching the coating and observing the healing of the gap for 36 hours with an optical microscope. As you can see On the top left of this slide, there is a total healing after 36 hours in room conditions. And the polyurethane-based microcapsules loading was 7.5 weight percentage. Now, on the top right of this slide, we have the self-cleaning performance that was also evaluated according to the water contact ankle test standard. The formulation exhibits 52% self-cleaning activity after being irradiated with UV light for 36 hours. And on the other hand, there is no self-cleaning performance observed in the absence of light, as you can see on the right graph. And the concentration of titanium dioxide of P25 grade was 0.4 weight percentage, but there was also anatase and rutile titanium dioxide nanopowder in a concentration of another, in total, 0.4 weight percentage. And finally, regarding the anti-molding activity, antifungal activity, this was measured according to the resistance to fungal growth test. The relevant factors in the formulation can be seen on the right bottom of the slide. We had 0.002 weight percentage of silver ions, 0.4 of titanium dioxide, 0.0015 of an antibiotic, and 0.4 titanium dioxide of P25 grade. And the formulation reached category 1. That means that we had less than 1% of the area covered with algae after 4 weeks of visible radiation, as you can see in this graph. And on the other hand, we had also very good antifungal activity in the absence of light. Moreover, the Slovenian National Building and Civil Engineering Institute, ZAG, conducted bond strength, capillary water absorption, and water vapor permeability tests in the coatings that showed acceptable results in every case. And finally, the evaluation in real environment is ongoing at the moment. However, the first results after 6 months in the tunnel in Spain showed an overall maintenance of the properties regarding the self-healing properties, as can be seen from the photos on this upper right, regarding the anti-molding activity, which is maintained in category 1 for every specimen that we tested, and also regarding the self-cleaning performance, which is similar again in every specimen that we tested, with a fresh polyurethane multifunctional coating that has been used as reference. And this was all from our side regarding the multifunctional coatings. Thank you very much.
Thank you, Maria. Thank you all the speakers in this part of the session. We will now have 5-minute breaks. We are good on time, so let's start at 11:55 with the presentation of the demonstration of these technologies. I would like to encourage all the attendees to use the questions option and send any questions they have our way. We'll be able to answer them either within this session or directly. So see you at 11:55 with the presentation of the demo site. Thank you very much. Welcome back, attendees and speakers. Let's continue with our session. Our next topic will be the demonstrations of the EnDurCrete products, and it will be presented by Irina Stepanovic, a Managing Director of Infraplan and Visiting Assistant Professor at University of Twente in the Netherlands. Irina, the floor is yours.
Thank you very much, Susanna. First of all, I'm presenting in the name of the large group of partners and people involved in the organization and performance of the demonstration sites, as we will see in the next slide. We have already seen in the first presentation by Arno that we had 4 demonstration sites across Europe, representing demanding and quite different environmentally challenging locations and different types of the structures. So we have involved actually from the Mediterranean climate over the ocean climate and Nordic climate, the structures exposed to the marine environment, as well the tunnel structure exposed to the carbonation and chemical attack. The demonstration projects, the purpose of them, as also mentioned before, is actually to test the EnDurCrete technologies, which included different types of cements, different types of additions or admixtures used in the concrete production, such as corrosion inhibitors, carbon-based green microfillers, textile reinforcement, and multifunctional protective coatings. We have used at the sites different sizes and different types of specimens, so we tried to simulate larger structural elements, but as well we added a large number of small specimens which are used for monitoring and the determination of mechanical and durability properties over the time. And at all sites you will see there are actually different monitoring techniques involved, either through the embedded sensors or through the embedded fiber optics or different types of monitoring techniques, and as well the environmental sensors for the local climate monitoring, and then as well non-destructive and destructive testing of the smaller specimens. The first site I will present is the offshore platform in Norway, which was led by the Kværner, now Aker Solutions, and the contributing partners were ZAG, Acciona, RINA, AM Solutions, and Nuatesi System. The demonstration site in Norway was, as you can see, located at the South Norway site at the marine location, and it included 2 types of offshore concrete that were produced actually from the EnDurCrete offshore. We called it EnDurCrete offshore concrete with newly developed cements, so CEM2 CMSLL, and compared to the reference offshore concrete CEM1 52.5R plus additional 5% of silica fume. Maybe just to give a small note, the reference concrete was a little bit unfair, I think, to the EnDurCrete concrete, but we can discuss it later. So the water binder ratio was also very low, 0.46, and relatively high binder content. The exposure zones, we could say actually there are 4 exposure zones. So we have 3 marine exposure zones, XS1, XS2, XS3, and additionally we have a frost, which in the coldest months the temperature goes up to -8 degrees. There were exposed 15 concrete panels with a size of 50 centimeters, 50 by 50 by 15 centimeters. And those panels included different technologies, so textile reinforcement with optical fibers, corrosion, electrical resistivity sensors, and different types of coatings. Additionally, there were cubes located in all those different environmental conditions. You can see how the site was established. So there is a steel frame formed on the board structure, and there are panels which are exposed in the aerial, tidal, and the submerged zones. And on each panel, there are dedicated different technologies involved. Additionally, the tests, so the site was established in September 2020, and we have actually very fresh results after 12 months. The tests included the compressive strength, the porosity analysis, chloride penetration tests, and then salt frost scaling, and as well the sampling for the contact angle measurements. You can here see some of the results. So the detailed results are presented in one of our last deliverables. The panels were used for drilling the cores, and as you can see on the core here, the chloride penetration tests were performed on both sides, and then the middle core was used for the concrete compressive strength determination. Generally, we can see that the reference concrete had higher values than the EnDurCrete offshore concrete. As I mentioned before, probably unfair competition with 52.5. Nevertheless, the EnDurCrete offshore concrete quite well performed regarding the frost and the permeability measurements. As well, the coatings performed really well. The frost freezing thawing testing results are presented in this graph. As you can see, again, reference offshore concrete performed a little bit better, but overall, all concrete samples performed very well regarding the frost degradation problem. So generally, the EnDurCrete offshore concrete had a lower permeability than the reference concrete, and the total air content was varying between 5 and 6%, which is a very good prerequisite to be frost resistant. Chloride penetration tests showed no apparent difference in chloride penetration between the offshore reference and offshore EnDurCrete concrete after 12 months. The highest chloride content was measured in the splash zone and the submerged zone. The treated panels also show minor presence of chlorides up to 5 millimeter depth. The measurements using the electrical resistivity sensors performed by ZAG did not show any significant corrosion activities. And contact angle measurements of waterproofing membrane, which was performed by Acciona, showed good wettability of the surface, implying that its hydrophobic properties are as expected. The second demonstration site is a marine port in Spain, which was led by Acciona, and contributing partners are Novatesi Systems, AM Solutions, iBox, Vito, Heidelberg Cement, and Sika. The location of the demonstration site, as you can see, is in North Spain, exposed to ocean climate. The prototypes of the samples were installed in a concrete dock called Port Gijón, El Musel, Spain, supported by the Port Authority and coordinated by Acciona. We can see on this slide how the steel frame was used for holding the panels in different zones, from aerial zone, tidal zone to the submerged zone. In this site, there were used two cement types. First of all, the reference cement was CEM3A 42.5N, and the EnDurCrete cement CEM2CMSLL. Additionally, the technologies developed in EnDurCrete were used polyurethane coating, corrosion inhibitors, and biochar with recycled carbon fibers. You can see all the tests which were performed on those samples exposed to those environments, which included durability tests, carbonation, chloride, sulfides determination, and then compressive strength and monitoring with electrical resistivity sensors. On this slide, we can see the different samples from different zones, which is quite significantly different. So in the splash zone, we have a clean concrete surface. In the tidal, we have some algae formation, and in the submerged, we have some biological growth. Overall, the samples were performing very well. As we can see in the compressive strength, actually the EnDurCrete cement or concrete samples were achieving the same or even higher compressive strength comparing to the reference one. And as well in the penetration of chlorides and penetration of sulfides, the EnDurCrete concrete samples performed better than the reference concrete. The detailed results of the electrical resistivity were actually presented before by Margarita and Francesca. As we will go further, I will not go into details. So additionally, we can here see the results of the porosity and density and mean pore size. Most important is that both concretes performed really very well. Also, the water penetration was much lower comparing to the reference concrete. In the SEM scans, we can see that no significant difference in the microstructure, and overall impression is that EnDurCrete concrete had very low permeability. So in summary, the sulfates penetration was no recording in splash and tidal zones, and in the submerged zone, the best results were with EnDurCrete concrete with SEM2 CMSLL. The same was for chlorides penetration. The better results was recorded with the EnDurCrete concrete in all zones, as well for the carbonation. The bulk resistivity showed a moderate risk of corrosion for the reference cement and very low risk of corrosion for the EnDurCrete concrete. And in the SEM scans, there were no significant differences. The next one is also the demo site in Spain, again led by Acciona and supported by Nova Tesi Systems, AM Solutions, iBox, Vito, Heidelberg Cement, and Sika Partners. The tunnel is a publicly owned entity and owned tunnel, which used to be a coal mine, but it's out of the service, and it is used now as a research center and for investigation of different excavation techniques, spraying, shotcrete, etc. We have used it for placing our tunnel elements, as Paolo has presented already, and representing the exposure classes for XD1, moderate humidity, and XA2 for moderate aggressive chemical environment. In the tunnel, there were placed tunnel elements, the panels, large size, and there are 60 small specimens for different purposes of the test, and also for including different technologies. As presented also before, here were used the inhibitors and the CAR and the coatings. We can see here, so the preparation of the samples. The preparation included the usage of the textile reinforcement and fiber optic sensors. This is the two-stage loading before the placing the panels in the tunnel. As well, initialized cracks were performed in order to test the computer vision technique for detection of the crack location and the width. And as well, the device for measuring the surface roughness was applied. In this slide, we can see the testing of the coating, which was presented by Maria, so I will not go into details. What's important to say that the coating showed very good performance in the self-healing, self-cleaning, and anti-molding properties. Finally, for the durability tests, we can see very high compressive strength from the EnDurCrete concretes, which were produced, I didn't stress, with the SEM6 SV, and compared with the reference concrete produced with the SEM2 AS 42.5 R. The porosity measurements showed very similar results with very high number of pores, but the mean pore size around 0.04, 0.02 micrometers, which means a very high resistance to the frost. And as well, the penetration of the water was much better, or no penetration at all recorded with the tunnel EnDurCrete concretes, as well with the addition with the biochar and comparing to the tunnel reference concrete. No sulfates penetration was found in any of the mixes, and as well the SEM scans showed no significant differences at the microstructure level. And the last demo site was a Kirk Bridge in Croatia, which is located at the northern part of the Adriatic coast, led by Infraplan and ZAG, and contributors were Heidelberg Cement, AM Solutions, SEA, and NTNU. So you can see the location of the panels, which was under the Kirk Bridge, connecting the mainland and the Kirk Island. It has two arches, and we are actually located at the platform which was used for the production of the elements at the initial site. Construction site. The 5 materials were used at this site, so there were 3 cements, both presented in the tunnel and the marine environment, so 2 EnDurCrete cements, and additionally 1 set of samples was coated with 1 polyurethane coating, and we had 2 reference cements as well used for a marine and the tunnel environment. 2 types of corrosion sensors were used, so coupled multi-electrode system and electrical resistivity, which will be shown on the next slide. We have 3 zones of exposure: submerged, tidal, and the splash. And altogether, we had 12 columns and 56 cubes in different exposure zones. The columns are 3 meters long, as you can see on this picture. This is a little bit displaced, but okay, we have submerged zone at the bottom, then we have a tidal and the higher or longest splashing zone. On this side, you can see the temperature differences. So it's the typical Mediterranean in a sense that it can get very hot, but also it can be relatively cold because of the alpine influence in this northern part of the Adriatic coast. We had continuous corrosion monitoring with the Wi-Fi data acquisition system and as well environmental monitoring. And periodically, we are performing durability tests using the samples which are exposed at the site for chloride profiles, for porosity, mineral phase change, mass, and ultrasound velocity and eigenfrequency. Here you can see the production of the columns at ZAC. In each column, there are embedded 5 ER sensors along the length of the column and 16 couple multi-electrode sensors, not in all the columns, which are used for the measuring the corrosion currents between exposure zones over the period of time. In each column, there are 4 reinforcement bars, which will be used once we decide to, or once the significant corrosion activity is recorded. They will be used for demolishing and doing the detailed visual examination of the rebars. You can see some of the results of the chloride penetration tests. Very briefly, so the chloride surface content is highest at the splash zones, as you can see in both concrete and EnDurCrete concrete and the reference marine concrete used with the reference cement. Generally, we can see a very low diffusion coefficients and on very similar behavior from both EnDurCrete and the reference concrete. These are the scans which will be explained by Clark here from NTNU. So the scans are actually confirming our chloride profile tests. Here we can see as well some of the results of the corrosion monitoring. Corrosion monitoring is continuously measured, as I said, with the embedded sensors and with the Wi-Fi data transition system. The couple multi-electrodes are along the whole length of the column, and you can see a little bit higher activity in the splashing zone, but this is still very low, almost insignificant corrosion activities. With the ER sensors only on the column 4, there is one ER sensor showing that there is some loss, but again, very minor activity. This one is probably an error, and one of the columns was slightly displaced at the bottom. So what we can conclude, there is no significant corrosion activity to make final conclusion about different materials and exposure zones. Only different current fluctuations among different columns, as said, and no evidence stable anodic and cathodic currents. Very minor differences in durability properties, and we can conclude that new cements are comparable to reference cements, which were CEM2 AS 42.5R and CEM3 42.5N. And to mention for all our demonstration sites, as you can imagine, they are we have results after 12 months and after 18 months for Kirkbridge. They are not sufficient to make final conclusions. So all our demonstration sites are continuing measuring and performing monitoring results after the end of the EnDurCrete project. Thank you very much for your attention.
Thank you very much, Irina, and thank you for taking up the challenge of presenting all 4 demo sites. We are very happy that you did. Thank you. Okay, and our next presentation, we are very happy to collaborate with the Resilience project and again have them present at our event. Our next speaker is Liberato Ferrara, professor at Politecnico di Milano, Italy, and coordinator of the Resilience project. Liberato, the floor is yours.
Okay, thank you, Susanna, and thank you very much for having invited me to this final event of the EnDurCrete project. Twin project. We have been working together in dissemination events throughout the years that we have been working on. Okay, it seems that I have the control. So I want just to give you an overview of the activities that we have performed in this framework, just trying to frame them into what we call the sustainability strategy that we have adopted throughout the duration of our project, which works according to a three level, which goes from product to process to context. And just a quick reflection on the challenges that we as civil engineers have to face nowadays also to meet the sustainable development goals of the United Nations or the decarbonization goal, which we have been reading and speaking about too much in these years. Actually, we have to focus on how to build sustainable infrastructures, long-lasting, considering the positive outcomes that they can generate on the economic growth of our communities and our societies, but also considering the need of refurbishing existing infrastructures, because actually traffic interruptions and delays that we have likely experienced several times during the past years, each year cost every household $3,600 USD of just money outgoing. And then we have to look into the coastal protection, which can be challenged by climate change events. These are events in Malta Island. These pictures are taken from a Malta newspaper. So in a Mediterranean climate, you can have these extreme events which challenge our structures. Consider that Europe has 66,000 kilometers coastline, and about 700,000 European Union citizens live in areas exposed to coastal flooding. And this is becoming even worse considering the sea rise due to climate change. Decarbonization goals, we have to improve and make more efficient and economic viable the use of renewable energy sources. These are two specific sectors that we have tackled in our resilience project. One is geothermal energy. We have several areas in Europe which are producing this kind of energy. There are remarkable examples. For example, last week I was reading at the German pavilion in Expo 2020 in Dubai that the city of Munich is completely autonomous in this sense because it completely goes on geothermal energy. And we have also to go farther with offshore wind energy harvesting, and this is also a sector that we have tackled in our project, together with the blue growth. We live on a planet which is called Earth, but actually only 5% of, but 70% of it is made of water, is made of sea. And only 5% of our economy and of our food, for example, comes from the sea. So there is the need to really take much more from the sea and leave the earth to rest a little bit because it's now depleted. And in the blue economy sector, there are emerging sectors that can really also drive the recovery of the economy and of the society after the pandemic. But whenever we go in environments like the one that I have mentioned, and we go to the sea, we go to aggressive environments like the one in geothermal drilling, we need durable and resilient infrastructures. These are pictures which are iconic by themselves and can show what can happen with structures in offshore or in sea environment. They can undergo severe deterioration problems. With accidental extreme events, they can be completely destroyed with economic losses, considering also that you lose the structure, that you lose what the structure was built for. This is a platform for mussel farming, so you lose the platform and the harvesting, and it's quite a huge loss for the companies. And this is an example of what we demand to our infrastructures in geothermal energy plants. This is a cooling tower structure. So you see this water is rich in sulfates, is rich in chlorides, and there is the abrasion due to the rain. This is the service condition for 364 days per year. The structure rests only 1 day per year for the maintenance. And this can be the consequences due to corrosion of the concrete, of the matrix due to the sulfates. So this was the scenario, and when we go to the design codes, we actually find only prescriptions based on minimum cement content, maximum water cement ratio, and so on. But these prescriptions, actually, if we go to modern concrete, high performance concrete, or even ultra high performance concrete, they are automatically guaranteed. So we do not have really a performance-based durability design framework, which can help us also in promoting the innovation in this sector. So this was the context in which we, as Resilient Consortium, gathered and applied. The project started in January 1st, 2018. We are going to finish in a few months from now at the end of March. 13 partners, 3 linked third parties from 7 European countries. And as you can see, these are the partners of our consortium. We cover the whole value chain of the concrete construction industry, from the producers of constituents to engineering consultancy companies to precast construction, large-scale infrastructure companies, and large-scale end users. And we have 6 universities in the consortium, and I am the coordinator with Politecnico di Milano. So, as I said, our goal is to work on product process concept. We have developed the concept. It's not a branded material or a specific material, but it's a mixed design concept, the material concept. We call it ultra high durability concrete, and the methodology for durability-based design in order to tackle our problem of designing longer lasting structures in extremely aggressive exposures. Sorry, there was a movie here which was made in our lab. We started with technology of ultra high performance concrete, ultra high performance fiber reinforced concrete, and we engineered its composition using micro constituent, nanoscale constituents to promote self-healing, to promote self-curing, to have a very extreme, I will say, control of the crack width, because we were able to control width of our cracks in the range of a few tenths of microns. We use alumina nanofibers, cellulose nanomaterials, and crystalline admixtures for self-healing. Here are some examples. On the left, you have a conventional concrete, chloride penetration. On the right, you have our materials. This was developed in Valencia, Universitat Politecnica de Valencia, and you can see with our materials, not only you have very narrow crack, the penetration is limited at the very beginning of the cracked surface life, but with the healing, you almost reduce it to zero. You do not see any more chlorides in the material. And you can see here some visual images of the crystalline growth in the cracks, which are completely closed, and the comparison of the technology that we have used in our project are the green curves in these graphs, with other technologies to promote self-healing, for example, the superabsorbent polymers, which are the purple curves, or the reference material, which are the blue curves. So in our case, was always much better. Also for large crack widths, more than 100 microns. We also checked, because we wanted to explicitly exploit this in the design, what self-healing means in terms of ability of the material to maintain the mechanical properties a long time. So with repeated cycles of cracking and healing, which is what the structure will experience. And we also went into microscopic investigation to check the efficiency of the healing on the fiber matrix bond, as you can see from these graphs. So, and these are some images of the effects of the nanomaterial, the nanoalumina and the nanocellulose. You can see that the dots representing this material, the blue, the green, and the red, in all cases, we had the better self-healing and the better recovery of impermeability versus water capillary absorption. So what we did with the materials that we developed, as I said, it's not a unique material. Each material was designed with specific reference to the pilot and to the conditions that it had to experience. We built, and we are currently monitoring 6 full-scale pilots. 2 of them are in Italy, in a geothermal site. 2 of them are in Spain. 1 is in Ireland, and 1 is in Malta. We tackled the sector that I said before. This is the pilot in the Galway Harbor, is a raft for mussel farming. It's floating, and we have also a camera which is streaming 24 hours live, so we can inspect the prototype every time, and periodically we go to it to inspect the cracks and the healing. Some of the beams this prototype consists of were pre-cracked. There were different level of pre-stressing to check the efficiency of the material in different conditions. And this is an image of when the pilot was floated in May 2020. This is the second pilot, is the floater in scale 1 to 2 for an offshore wind tower. It has been anchored to a quay in the harbor of Sagunto, still in Spain. Rover Maritime is responsible for this together with University of Valencia, whereas for the other prototype, the company RDC was responsible. And we visited it. You can access the pilot with a bridge made with the same material, and you can go inside the pilot to inspect, and there are different sensors installed to check the healing, to check the corrosion of the ordinary reinforcement. You can see we visited it in occasion of an international conference, several people going up to this ultra high durability concrete bridge that we built. This is the Irish pilot. It's made of 3 different cells. The first one, the biggest one that you can see in the forefront of the picture, is exploiting regular concrete technology, whereas our material, in this case, the technology is ultra high durability matrix with textile reinforced, whereas in the previous pilot was dispersed fiber reinforcement. You can see the saving of material that you can have. Obviously, you cannot go too low because of the buoyancy requirements. The pilot is now in the Galway Harbor. These are some of us visiting it, and there is also, you can see here where the mouse is indicating, there is a box where all the sensors go with their cables and they wireless transmit to a control unit, which is in the offices in the harbor. And some images of the Malta pilot. This was an existing structure, a water tower, which was severely damaged, as you can see, and we retrofitted it, employing both ultra high durability concrete with dispersed fiber reinforcement, and for the drum with textile reinforcement. Some images of the finished structures. We also were able to go inside before filling it back once again. These are some images of the load test made to filling, and now the structure is in use in the Valletta Harbor area. And some images of the Italian's pilot. We built them on the site with a dedicated batching plant, which was brought on site. And this is a basin for the mud in service for the geothermal drilling mud in service of the geothermal drilling platform. And in this other case, this is a pilot meant to keep the water from the cooling towers. We designed this basin with 3 different technologies. We have ordinary reinforced concrete, 10 centimeter thickness. We have cast in place ultra high durability concrete, 6 centimeters thickness, and we employed a partially precast solution. You can see this during the construction. This was February 2020. The slabs were precast with holes and the cast in place columns in between them. The material also filled the holes and realized the connection. But in this case, the slabs were only 3 centimeters thick. So we have a 70% saving on the material. And these are some images of the finished basin and of load tests that we have been regularly performing and monitoring. You can see here the basin is completely filled, and you have some pictures here on the right. It's a little bit blurred, but it's the degradation of our ordinary concrete as exposed to disulfate water, and our UHDC material, which is very smooth and completely sound. And some pictures also you can see here, image of a quite large crack, was a shrinkage crack, which was completely healed with no detriment to the water containment capacity. Well, actually, if you go to the mixed design, people may quarrel, may complain that we are using a lot of cement and this may not be good for the sustainability. But actually, this is a not correct way, in our opinion, to look at it. You have not to look to the composition per cubic meter, to the carbon footprint per cubic meter. Actually, if you consider an ordinary concrete with 350, 400 kilos per cubic meter of cement, to realize 1 meter of the wall of the basin, which is 10 centimeter thick, you need 40 kilos of cement. But in our case, with this mixed design, to realize 1 meter of the basin wall, which is just 3 centimeter thick, you need 18 kilos of cement. So in the end, you have a more than 50% saving on the use of the material. So think of the structural unit, think of the functional unit, and not of the cubic meter of cement. And most of all, let us start thinking in terms of life cycles. We may have an additional higher cost, higher construction cost, but in the end, with reduced maintenance, the life cycle cost can be greatly improved. And these were demonstrated for our structure with significant saving on the life cycle indicators. So in the end, we embed the degradation models into the structural design, being able to arrive at the prediction of the end of life. Obviously, with this material, your end of life, it's quite long, more than 100 years. So you may ask, what does it mean? More than 100 years, because in that time, the contractor, the owner, the end user may go into changes of its needs. So we have addressed also the recyclability of our material. I will say we were a zero waste project because all the specimens which were produced in our lab were completely recycled, and we demonstrated, if we look at the graph in the right, with reference to the parent material, the yellow one, all the materials employing recycled material as aggregates were able to guarantee higher, if comparable, or higher compressive strength, flexural strength as well. But also we're able, these are results of PhD thesis going on now, also we're able to guarantee the persistence of the healing capacity also upon recycling. So which is the final scenario? This is a reflection paper addressed by the European community on the role of materials in the post-COVID society. And this is the vision that we take for our project for the exploitation after its end, to be able through advanced materials to create a less dependent and more resilient economy, guaranteeing raw material supply, higher material durabilities, higher energy efficiency, higher degree of material recycling. This is the welcome page of our website, where you can find all the information about the project. We have also developed the MOOC with the contents of our activity. There is a page where you go for dissemination, where you can find all our open access journal papers published so far. We published 13 papers as a consortium, and for most of them we have also open data. So you have all the data sets freely available according to the open data policy. As an educator, as a university professor, I am quite proud and happy to say that we offer to about 20 young engineers, young scientists, a starting career opportunity with PhD, with researchers, assistant professor positions in university. And we train, this is only in Milano, more than 40 students with their master thesis on this topic, because I think that this is also the way to have this material widespread in the market, training the future engineers to confidently use these materials. So these are my contacts, and also we are on the social media with Facebook, Twitter, LinkedIn, and our YouTube channel. Thank you on behalf of the Resilience Consortium. This is our last full plenary meeting in person in Valencia in 2020. We have go back to a hybrid meeting in September 2021. Until then was only online. And also want to thank you on behalf of my whole research group at Politecnico di Milano, and thank you all for your attention.
Thank you very much, Liberato, and the Resilience Project for the collaboration. We are very happy to have you. And now moving on to the Q&A session. Our speakers have prepared answers to frequently asked questions, and we have also some polls prepared for you to vote in. So the first topic of health and safety will be presented by Cecile Filippo, a project leader at the nano safety platform of CA Renewable. The floor is yours. Please unmute yourself. Thank you. Still muted. Could you please switch to another microphone, or maybe use different audio?
Do you hear me?
Yes, now we can hear you.
Okay, perfect. I will just, okay. So today I will speak about all the health and safety aspects, and also the environmental impact and the recycling aspect on you. It's an important issue to take into account when we create and use the new materials. So for that, we have to, sorry. The next slide, please. Thank you. So we have to to have a global vision of all the life cycle of the product to address these three main topics, the health and safety, environmental impact, and the recycling aspect. So for that, we have to analyze each step separately and see their role and the impact. So for that, on the next slide, please, we see that, for example, for the health and safety aspect, we have focused the analysis on the production step. So in this case, in the Undercrate concrete, new materials are involved, such as nanomaterials. So it's important to update the risk assessments regarding this, the use of these new materials. I've also looked on the regulation regarding the use of this product. And like that, we are able to update the risk assessment, adjust the protocols, propose some mean of prevention for the worker exposure, adapt also the training of the workers, and propose some guidance to be sure that the product can be handling in safety. Next slide, please. So the second pillar that we analyzed is the environmental compatibility of the product. For that, we are focused on the two last steps of the life cycle of the product during the use and the recycling scenarios. It's important that the product is in compliance with the environmental law and avoid any leaching of organic pollutant or heavy metal from the material to the environmental. So for that, tests have been performed on the different Undercrate concretes, and we have seen that in all of the case, the product are compliant with the regulation, and we don't see any contamination in the environmental. And the last point is the recycle aspect. On the next slide, please. So for that, it's important to know that after the life services, concrete structure are usually demolished and crushed into pieces, and then the rubble can be reused as aggregate in a road base, for example, or in new concrete. So for that, we have to check that the Undercrate concrete are also available to this recycling practices. So next slide, please. So for that, we have checked that the Undercrate concrete can be recycled by the conventional recycling facilities. So this is okay. And on the next slide, we have also controlled that the technical characteristics of the Undercrate RCE are also equivalent to the reference one, and is also the case. So at the end, we have seen that it's okay, the Undercrate concrete could be seen as safe to use, environmental friendly, and also recyclable. Thank you for your attention.
Thank you very much, Cecile. The next topic on pre-validation of the technologies will be presented by Professors Chidevert and Alissa. Go ahead.
Yes, thank you very much for the introduction. So my name is Alissa Machne, and I will guide you together with my colleague Claire Chidevert from NTNU through a durability-related part of this Q&A session. So the two topics we are talking today about were not just performed by NTNU, but also by CEA and SAG, but Claire and me are the presenters today. I want to warn you first that this section might be a little bit more interactive. We have two polls up for you shortly, where you are asked to give us your opinion on the questions we ask you to make this a little bit more interactive. So be prepared. So first of all, I'm going to talk about carbon. No, please not the poll yet. No. First of all, I'm going to talk about the carbonation part of the durability investigations in the EnDurCrete project. Within the project, CEA developed a model, a carbonation model amongst others, and SAG and NTNU were asked to provide experimental data to calibrate and verify this model. So in the beginning of the project, these three project partners were sitting together discussing what should we take into account, what parameters does the model need, and how can we obtain these results or these parameters from the laboratory tests in the best possible way. So there were a lot of discussions up and running on various parameters and how to test them. And now we can start the poll, because we were thinking, okay, if you have to choose one parameter, which of them would you take for sure into account? We have answers from A to E, and we could start the poll now. Hilda, could you start the poll? Yeah, now it comes. So from a lot of different parameters you can choose. If you have to choose one, which one would it be? Relative humidity, drying rate, cement composition, CO2 concentration, or the water to cement ratio? We have kind of half a minute for this poll, so just take the one that sounds most important for you in a short, as a first step or a first idea. Okay, I'm not sure if we can, now we can see the results. So most of you took into account the cement composition and the water to cement ratio. Second most is then relative humidity and the CO2 concentration, and actually nobody chose the drying rate. Okay, we can proceed with the presentation, because instead of just giving you one answer, and spoiler alarm, there is not one answer to that question, I would rather show you how we approached that when we were sitting together in the beginning of the project discussing that. So what we did is that we got mortar and concrete prisms. They were prepared by Acciona and then were sent to the NTNU and the SAG laboratories. And these prisms, we, or half of them, we cut in thick blocks. Of the prisms, we know the cement composition. For sure, we have a cement producer on board on this, in this project, but also the mortar and concrete recipe or mix design. So aggregate types, particle size distributions, the water to cement ratio, the admixture content, all of that was known. So half of these prisms we cut into thick blocks and we carbonated them. We carbonated them at 60% relative humidity and 1% CO2 concentration for various times. And at these various carbonation times, we took blocks out of the carbonation chamber, actually split them, and then on one part, we determined the carbonation depth, as most of you know, with a pH indicator, spraying the surface and reading the carbonation depth, either manually or with image analysis. And then the other part, we profile ground inwards, so we get powders from various steps towards the inner of the sample, and these powders were analyzed with TGA, so we got an idea about the portlandite content and the calcite content at these various steps. So from this part, we got a pretty good idea on the carbonation development over time, because we did that at various carbonation times. And then on top, we also, the other half of these prisms, we cut into thin discs. And half of these thin discs we carbonated fully, and the other half was stored almost CO2-free, a very CO2-poor atmosphere. We then sealed all the non-cut surfaces of these discs and performed drying experiments in them. So we dried them to various relative humidities, always measuring their weight to get an idea of the drying rate. We resaturated them and dried them again to also get an idea of the porosity of the carbonated and the non-carbonated samples. All of this input actually yielded in a pretty good carbonation model. You see that here on the bottom of the slide, where in red you see the modeling results, and in blue and in yellow you see our experimental results of the carbonation depth, either determined manually by measuring them with a ruler or by image analysis. So in a nutshell, this effort we took by taking actually all the parameters we had as possible answers before into account made us able to set up a really good model and confirm that with some experimental data on top. I have to say that this model also works for various cement compositions. So this is the result of the EnDurCrete binder, but of course we tested that also on our references. With that, I'm finished with the carbonation part we wanted to talk about, and would give the word to my colleague Claartje de Weert, who will talk about chlorides.
Thank you, Alisa. Do you change the slide, Alisa? Yes, thank you. So besides carbonation, we also looked into the chloride ingress in concrete, and the concrete's developed in EnDurCrete. And as most of you know, chlorides originate either from seawater or the icing salts, and they can ingress into the concrete cover. And when they reach a sufficiently high concentration in the vicinity of the reinforcement, they can cause corrosion. And it's actually this reinforcement corrosion which is considered one of the main degradation mechanisms for reinforced concrete exposed to seawater or the icing salts. And if our EnDurCrete concrete is supposed to be durable, it has to have a good resistivity or resistance against chloride ingress. So I just have a couple of slides where I'm going to take some examples, and we're going to look into the concretes which have been exposed at the Kirk exposure site, which Irina already introduced to us. And we scanned these with a micro XRF after they had been exposed for 1 year. And this exposure site, as some of the others used in this project, has the advantage that we can test different exposure zones. And again, a little poll to check whether you're following and you're all awake. And Irina actually already gave a little hint on what the correct answer is to this question, is which exposure zone do you think is most susceptible to chloride ingress? So is it the submerged zone, the tidal zone, or the splash zone? So could build up launch the next poll? Thank you. So please vote where you think you would have the deepest chloride ingress after 1 year of exposure. Would it be in the submerged zone, the tidal, or the splash zone? Thank you. Wonderful. So the poll indicates that the ingress is or we also expect that Ingress is deepest in the splash, followed by tidal and then submerged. So thank you for these answers. Let's go and look at the results. Can we? Yes. So here we have concrete samples ZAG and Infraplan had retrieved from the Kirk exposure site, and they sent them to us at NTNU to do some micro-XRF scanning. So the top 2 rows are the reference concretes that were exposed, and the bottom 2 rows are the concretes developed in EnDurCrete. And if we look at the columns, we can see that on the left we have the submerged samples, in the middle the samples that were exposed to the tidal zone, and on the right we have the samples exposed to the splash zone. So if we go to the next slide, then we can see our chloride maps. So I have to say that all these samples have been exposed from the bottom to chloride. So chlorides have ingress from the bottom part of these samples inwards. And in order to make the ingress depth of these chloride maps a bit clearer, I've added on these little white bars that give you an indication of how deep the chlorides have penetrated into the concrete. Yes, these little maps, these little white bars, and also an indication of which depth they represent. And if we look at the exposure, so the answer to the question, we look and we compare the columns, the submerged samples, the tidal, and the splash ones, we actually can see that the samples exposed to the splash zone tend to have the highest ingress. So the splash seems to be the worst zone, at least at the Kirk exposure site. If we then compare the different concretes, so if we compare the reference concretes, the 2 top rows, compared to the EnDurCrete concretes, there are actually no large differences. And that's also what Irina has been presenting when she was presenting the results from the exposure site. Actually, our EnDurCrete concretes are more environmentally friendly concretes, are performing similar to the references. So that's a very good thing. They're more environmental friendly, but they're actually as resistant as the references to chloride ingress. So this is a sneak peek of results. And as Irina also said, these are results after 1 year, and we're very interested to follow this up together with Infraplan and ZAG, this exposure site, and see how this chloride ingress develops over time. And we will compare that to laboratory experiments we've done parallel on these concretes as well. And nonetheless, we want to compare that with the model CEA has developed for chloride ingress, because they have developed a very advanced model. It's a multi-ion model, which actually could account for these different exposures, because they will account also, for example, for leaching. So it's a very promising model, which we've already verified in the lab, but it would be really great to be able to verify it with this field exposure on the long term as well. So we're looking forward to also beyond EnDurCrete on this collaboration. So stay tuned.
Thank you.
Yeah, thank you.
Thank you very much for the presentation. Next, we have the durability modeling presented by Ruben, a civil engineer at RINA Consulting. The floor is yours.
Hi, good morning, everybody. My name is Ruben Valsecchi from RINA Consulting, and today I'm going to speak about the modeling of durability over 100 years. So basically, the very first question that we have to think about in order to speak about this topic is which materials or combination of them lead to the highest increase in service life. In the first case, we analyzed the concrete diffusion, and in order to make that, we analyzed 2 different kinds of structure. The first one is a reinforced concrete pier, and the second one a reinforced concrete dissipation box, both in a marine environment. Basically, here we analyze the critical pile element for the first structure and the critical external wall for the second one in order to evaluate the service life of this structure. So in this case, we obtain the evaluation of the service life. And in these two different figures, we can see that the use of the materials described so far, like the EnDurCrete, and the coating developed during this project, and the EnDurCrete with the use of the nanoclay inhibitors, lead to an increase of the service life of both the structure, and with an average increase of 16% for the by the use of the EnDurCrete concrete. And with we can go up to 25% using also the coating, and using the nanoclay inhibitors, we can have a huge increase, up to 42% increase of service life in average. For the second phenomena analyzed is the carbonation. This phenomena is assessed for in 3 different structures. The first 2 are 2 different concrete tunnel in continental environment, and the third one is a reinforced concrete bridge in a continental environment. Also in this case, we analyze for the first 2 structure. Basically, we check for the critical section in the lining of the tunnel, while in the third one, we check for the critical pile element between among the 3 different piles in the structure. In this case, for the carbonation, we can see here that a huge increase in service life can be reached by using the EnDurCrete cement instead of the reference one. And in average, we can reach a 45% increase on service life. So we can see that the use of EnDurCrete and also the implement of the nanoclay inhibitors can lead a very high increase in service life. The second question that we will have a look is basically which parameter have the highest influence on the service life evaluation. Basically, here we can see that the 3 different the most important parameters that have an influence of this evaluation are the factor of safety of the concrete section, the relative humidity related to the environment in which the infrastructure is located, and the concrete cover of the rebar of the section. For the carbonation case, we can see that the influence can go to high, from high to fundamental for all these 3 different parameters. This is simply related to the fact that carbonation, the 2 different mechanisms that play the fundamental role in the carbonation are the rate of corrosion and the penetration of carbonation, that in terms of time are basically the same. While for chloride penetration, we can see that only the concrete cover show a fundamental influence on the evaluation of the service life. This is related to the fact that the corrosion related to chloride penetration is very high, so the time needed for the corrosion can be seen as negligible respect to the time of penetration of chlorides. So since the concrete cover is the main parameters that can influence the chloride penetration velocity, so in this case is the most important one. And so the concrete cover can be assessed as the most important parameter for both this type of attack on concrete, while for carbonation, all the different parameters have an important influence on the evaluation. And that's all for me, and thanks for your attention.
Thank you very much, Ruben, for your presentation. Our last question and answer part will be on the life cycle assessment of the Undercrete cement, presented by Jakub Heller from Leonardo.
Thank you, Zuzana. And also thanks to all previous speakers. I have the honor to close this interesting webinar. And I would like to provide a brief summary of what we have done in frame of life cycle analysis, trying to answer the fundamental question: how environmentally friendly are the new cements developed in EnDurCrete project, and also the products made of these cements. As already mentioned, to answer this, we have been working on life cycle analysis in 2 stages. First stage was dealing with cradle to gate analysis, describing the production of all new materials and comparing them to alternative or reference materials that are commonly used. And in the second phase, which is going to be finished very soon, because the project ends this December, and this is the final task of the project. So in this second step, we are assessing the real scenarios similar to the demo sites, covering the whole life cycle, including the use phase. And therefore, we are using the results also from this durability modeling carried out and presented by Rina. So unfortunately, we still do not have the final results, because we have received these inputs just recently, but I will present the results of the first phase. So if we compare the global warming potential measured in kilograms of carbon dioxide, which is the most important parameter in this analysis, and we compare of one with the alternative EnDurCrete cements, we can see that we have achieved a very significant reduction. And maybe you remember that in the beginning Arno was presenting that the target of the project was to achieve the 30% reduction, and actually all 3 cements achieved more than 40% reduction of carbon dioxide production. So we can say that this was very successfully achieved. And why? Because these new cements contain much less of standard Portland clinker than the ordinary cement, which is demonstrated here in the basic equation. What happens during the clinker production. And simply, if we use less clinker and replace it with alternative materials such as fly ash, calcium sulfates, or slag, this leads to the presented reduction of more than 40%. I would also like to remind that according to various literature sources, the cement production is responsible for from 6 to 8% of the worldwide emissions of carbon dioxide. So if only part of the overall cement production would be replaced by these new cements, you can imagine that this could really significantly contribute to overall reduction of carbon dioxide, which is being discussed for many years at various levels. So this is really very promising, and we can only hope that these new cements will be introduced to market and broadly used as soon as possible. But we have not assessed only the new cements, but also the other materials which were presented by the previous speakers. yeah, sorry, this is just a quick overview of the performance of the new cements compared to reference cement in other impact categories. And you can see that also in the other impact categories, in the new cements behave much better than the reference cement one. So we can say that in general, the new cements are really more environmentally friendly than the reference one. And now to the alternative materials, novel admixtures and coatings. I will not present here the detailed results, but we can say that the environmental impacts of these new materials during the production phase only are slightly higher, but if we consider the whole life cycle and the extended durability, their use certainly makes sense, because the extended durability leads to significant reduction of all environmental impacts and also costs. So this will be summarized in the final deliverable of the project, which will be due in December. I can say that this has been confirmed by our calculations, and also the recyclability of EnDurCrete concretes was analyzed, as already presented by Cecil. Recyclability analysis was also performed by Vito in terms of performance of the recycled materials, and similarly to the results of the partner resilience project, we can say that these new concretes can be fully recycled in the same way as standard concretes. So that's all from my side. And I would like to thank you for your attention and the organizers for organizing this webinar. Thank you, Susan.
Thank you very much, Jakub. Thank you for closing today's event. I would like to thank all the speakers and Arno, our coordinator, for the event. Of course, Build Up for co-hosting with us. There are many attendees. We are very happy that you are interested in the project. Of course, you are interested in what is coming next. The project is closing in December, so we are working on final video presenting the results. There will be final newsletter, final updates on the website, and much more. So definitely follow the project, follow it on all the social profiles on the website. You can subscribe to the newsletter to learn more. We will be updating all the channels also after the project ends with any news, any new developments and follow-up activities. Thank you very much, and see you soon.
Thank you all for joining.